Hey everybody, this is going to be our first video for chapter 3. You will notice we're starting with section 3.2. I decided since we were remote that we would just skip 3.1 as it is just a review of exponential functions anyway. So section 3.2 is rather large, so I'm breaking it into two parts, which means you have two separate homework assignments for this section. So for part 1, our focus is going to be on inverse functions. So to do this, we're going to eventually get to like how to take derivatives of inverse functions. But for now, we need to review what an inverse function is so that you actually know what we're talking about. So let's go back to pre-calc for a few minutes. It says for inverse functions, if you have two functions that are inverses, if the point AB is on the graph of f of x, then the point BA will be on the graph of g of x. Okay, so what you're seeing here is that there are companion points on functions and their inverse functions. And when I say companion point, I mean those 2 points obviously have something in common. They've just been inverted or flipped to create a location on the inverse function. So let's start something simple. The functions f and g are inverses. Given the table of values for f, can we create a table of values for g? We certainly can, because these are just ordered pairs that represent points on the graph of f of x. And if we use the fact that there are companion points, like I said, on an inverse function, then we can use that to help us create a table for g of x. Okay, so let me get my little table here ready. And it's a pretty simple thing. All you're going to do is you're going to label it first x and g of x. And then all of the points that you know on f would just be reversed or flipped to be points on the graph of g. So you would have negative 26 and negative 3. You would have negative 7. Oops, and negative 2, and then you would have 0, negative 1. So you're just flipping all the points, okay? So the y's become x's and the x's become y's. And that gives you a little bit of information about the inverse function g. Okay. Those two functions we just looked at in the tables actually do have equations to model them. F of x is actually x cubed plus 1, and g of x is actually the cube root of x minus 1. So we're going to do another thing, another kind of step in the process of working with inverses, and that is we're going to verify that these two functions are inverses of one another using the definition of inverse. And the definition of inverse says that when you take f composed with g, and when you take g composed with f, both times you'll get just an x left. So I'm going to start with the left side, and I'm going to take equation g, and I'm going to be composing it, which means plugging it into equation f. So that's going to be equation g is this one here, and I'm plugging that in to equation f. All right, so let's see. It's going to be the cube root of x minus 1. I need cube root cubed plus 1. The cube root and the cubed would cancel each other out, so you would just have x minus 1 plus 1, which just equals x, and that's what the definition of inverse says should happen. Let's try it the other way. So we're going to try what happens if f gets plugged in to g. So if equation f gets plugged in to equation g, let's see, that would be a cube root. Can't find my pen. There we go. It would be a cube root of x cubed plus 1 minus 1. And then we're going to work on the inside. Obviously, the plus 1 and the minus 1 cancel each other out. And cube root and x cubed also cancel each other out, leaving you with just x. So just this simple algebra process allows you to verify that those two functions are in fact inverses of one another. So we know that the points flip in inverse functions. We know the composition equals x in inverse functions. Now let's look at graphs. So in graphs of inverse functions, you're also going to see some symmetry. Okay, so you should notice that the red line and the blue line are symmetric to one another along this dotted line. And I actually want to write down real quick. The red line is the x cubed plus 1 function. If you notice, it's the cubic functions moved up 1. And then the blue is that cube root function that we've been looking at, which was cube root of x minus 1, I believe. These 2 points are reflected across the line y equals x. And what that kind of means is that there are companion points, as we said before, where they are reflected across the line. So they're like the same distance away from this black dotted line. Okay, so this point is at 0, 1, and then the blue point is at 1, 0. At the bottom it says, what do you notice about the domain and range of these functions? Well, what happens is the domain and range also flip on inverse functions the same way that they flip with the ordered pairs, like we saw here. So the x's become y's and the y's become x's, right? Well, the domain becomes the range and the range becomes the domain when you're dealing with inverse functions. One other quick important note about inverse functions. So in order to create an inverse function, your function first has to be 1-to-1. And we would have talked about this last year, but let me remind you what it means. 1-to-1 means that your function passes what we call the horizontal line test. Okay? Make a note of that. So you're going to check first to see if your function passes the horizontal line test or not. Okay? If it does, it has an inverse and you move on. Like example number 1, if I draw a horizontal line at any point through this graph, it's going to only intersect the graph at one point, which means it will pass the horizontal line test. So is this function 1-to-1? Yes, because it passes the horizontal line test. Okay, which means it has an inverse. Okay, that's the whole point of that. What if it doesn't? So like example 2, if I draw horizontal lines through this graph, it's actually going to cross the graph twice, more than once. So this one is not considered 1-to-1. It fails the horizontal line test, which means it doesn't have an inverse the way that it is stated. So what you can do, though, is to make an inverse. I'm going to write all this down so you have it for your notes. But to make an inverse for this function, you have to do a little extra work because it's not 1-to-1. The extra work is you have to restrict the domain. And restricting the domain just means you're basically going to cut the graph down. So think of it like this. This is a U shape, and because it's a U shape, it fails the horizontal line test. If I take half of the U away, the remaining part would then pass the horizontal line test, making it invertible. So we're going to restrict the domain of this thing to basically just include half of the current U shape, which would be from 0 to infinity. Let's look at another example with inverse notation. So this is saying if f of 1 equals 5, if f of 3 equals 7, if f of 8 equals -10, find the inverse of f at 7, the inverse of f at 5, and the inverse of f at -10. Remember, inverse functions have companion points. So I'm going to write it a little bit differently. I'm going to say instead of f of 1 equals 5, that means you would just have a point at 1, 5. And then f of 3 equals 7 means you just have a point at 3, 7. And then same thing with 8, -10. Remember, the companion points tell us that if F has, you know, these points, then the inverse has those same points but flipped. Right? So 5, 1, 7, 3, negative 10, 8. Now go back and look at what the question was asking. The question was asking for what is F inverse of 7? Well, F inverse of 7, that means when the inverse is 7, or the x value is 7 in the inverse, what's the y value? Well, look right here. The y value is 3. Okay, what's the inverse at x equals 5? It would be 1. What's the inverse at negative 10? It would be 8. So all you're doing is you're flipping the points to find the companion points and listing the y values from those. Okay, a couple more pre-calculus-y things and then we'll get to the calculus. One more thing you do need to know how to do with inverse functions is like finding the inverse equations when you don't have a graph or any other information given other than an equation. So I have the steps written here. This is like the book work or the book's steps, and then these are my steps down here. Whatever makes sense to you is great. I'm just going to walk you through an example. So we're finding the inverse for x cubed plus 2. The first step would be to switch the x and the y, because the x and the y values switch on an inverse function, don't they? Remember the ordered pairs and how they flip? The next step would be to solve your equation for y. So I would need to subtract 2. That's going to give me x minus 2 equals y cubed. And then I would need to cube root both sides. And so I would end up with y equals the cube root of x minus 2. And I'm going to change my notation back to the inverse notation. So this is the inverse of f is equal to the cube root of x minus 2. Okay. Last question with pre-calculus review stuff. Sketch the graphs of f of x and its inverse function on the same coordinate axes. All right, first thing I'm going to do is I'm going to try to figure out how I'm going to graph this thing. We do know transformations like up, down, left, right, hopefully from last year. So I'm going to try to use those to help me in my graphing process. I think it is going to be easier to graph if we actually rewrite this inside in a different way. So what I'm going to do is I'm going to rewrite it by factoring out a negative 1. Because I want the negative to be shown separately from the addition part. So when I do this, I can see that x has been added by 1, which is going to make the graph go left 1. And this negative on the inside is going to reflect the graph over the y-axis. And when I say the graph, I'm talking about the parent function, which is the square root function. So the square root function normally has points at what, 0, 0, 1, 1, 4, 2. So we're going to move it left. I'm sorry, we're going to reflect it first and then move it left. Okay, so if we reflect the point 0, 0, it stays. Go left 1 and you are here. If you reflect the point at 1, 1, it goes to this side, and then left 1 moves it to here. And then 4, 2 reflects to negative 4, 2, and then left 1 would be about here. So I think kind of like that. Okay, now we graph the inverse, which all we have to do to graph the inverse is remember the fact that the x and y values flip, and we're just going to graph those companion points. So if I have a point at negative 1, 0, then my inverse would have a point at 0, negative 1. This graph, my original, has a point at negative 2, 1. So my graph will have a point at negative 1. I'm sorry, 1, negative 2. And then that third point all the way over there was at negative 5, 2. So our inverse graph will have a point at 2, negative 5. And we're going to try to draw this so that it looks like it's been flipped over the y equals x line.